Hello, in this talk, we will present our work on probabilistic scalability analysis for real-time tasks with precedence constraint on partitioned multi-core. We consider a task model composed of n sporadic tasks where each task to I is characterized by a precedence graph Gi and the deadline Di and the minimum arrival time Ti. Gi is a direct acyclic graph. It is composed of ni subtasks related between each other by precedence constraint. Each subtask is characterized by probabilistic worst-case execution time Cij. Each edge may introduce a communication delay EIJK between subtasks to ij and to ik. The presented task model is executed on multi-core processor with M identical core. We use fixed priority and preemptive scheduling with the partitioned policy where each subtask is assigned to statically to the same core. We assume that the mapping between subtask and core is given. If two dependent subtasks are mapped to differing core, we consider a non-zero communication delay between them. Otherwise, we assume that communication delay is included in WCUT and then it is neglected. Previous work have considered similar task model but with deterministic execution time. In Palencia and all work, authors use iterative equations for estimating response time of parallel tasks on distributed systems. They assume that all higher priority tasks are released at every subtask activation, but this assumption may be very pessimistic. A more recent work of Fonseca and al. Studied the execution of all possible paths in the graph and modeled them with self-suspending tasks. An exact solution based on mixed integer linear programming optimization is used to deduce the response time of each DAG. This approach allows to reduce pessimism, but it requires a lot of computation due to the high complexity of ILP problem. In this work, we propose a new response time analysis based on iterative equations that avoid pessimistic assumptions and high complexity. We also extend it to probabilistic task model. To compute the response time of a given subtask, we proceed in several steps. First, we compute the local response time that consider only the effect of predecessor subtask. Recursively, we update the response time of successor subtask by the maximum response time over predecessors and by the internal interference IIL exerted by parallel predecessor subtask on each other. Therefore, this interference equal to the convolution of execution time distribution CIK of parallel and predecessor subtasks. Second, we compute the response time in isolation that consider only the effect of subtask from the same graph and that neglect the effect of higher priority DAG task. To obtain the response time in isolation, we add to the local response time the effect of parallel subtasks that are not predecessor. Finally, we compute iteratively the effect of higher priority DAG task to obtain the global response time. We compare our deterministic analysis to the holistic approach of Palencia and to the mixed ILP approach of Fonseca. We note that in average our analysis overestimate the exact response time obtained by MELP more than 1.5 time, while the holistic approach overestimated 2.5 time. On the other hand, the MILP approach required much more runtime than our analysis to accomplish the computation. In average, it takes more than 30 times what our analysis take. For the probabilistic analysis, we run our analysis on 100 generated task set. We note that the number of task sets that are schedulable with high probability, about 18 and 19%, is important. While the deterministic analysis will reject all these task sets. For future, we will work on heterogeneous processor, and we will also study the dependency between different execution time distribution. We invite you to find more details in our paper. Thank you.